Far beyond the familiar constellations, deep within the silent sprawl of Leo, a telescope suspended in darkness captured something that defied expectation. The James Webb Space Telescope, its golden mirrors turned toward the faint light of a distant sun, recorded a signal that would one day be remembered as the moment the universe began to answer back. Through its sensitive eyes, light that had travelled for more than a century arrived as data streams of invisible wavelengths whispering the story of a world that seemed impossible. Hidden within those patterns of infrared radiation was a rhythm, a pulse too deliberate to be random, too structured to be mere chemistry. When scientists first noticed it, the discovery seemed almost absurd. An atmosphere whose temperature rested at a perfect balance, neither scalding nor frozen holding, steady around 49 degrees Celsius, or roughly 120 degrees Fahrenheit. It was as though the planet itself had been tuned to sustain something delicate. The numbers emerged quietly, buried inside packets of data sent across millions of miles. For weeks, they appeared unremarkable, until subtle irregularities began to surface. What initially looked like statistical noise began to take on the shape of consistency, a fingerprint repeating itself across multiple observations. Somewhere in Leo, light was being filtered through gases unknown, bending and dimming in a pattern that no geological process could explain. The signal was faint but persistent, as if the cosmos itself were clearing its throat to speak. The first human to truly understand what that meant was an astrophysicist named Niku Medusan, a specialist in exoplanetary atmospheres working in the quiet halls of Cambridge University. One winter morning, as the chill of December mist clung to the city, he sat before his screen, examining curves of light intensity plotted across time. Each dip and rise represented a distant world passing in front of its star, blocking a fraction of starlight. But this time, one of those transits carried an anomaly, a spectral pattern, whispering of a molecule that shouldn't exist without life to make it. As Medusan expanded the data, his pulse quickened. The telltale imprint belonged to dimethyl sulfide, a compound found on Earth only where biology thrives. In the breath of plankton, the metabolism of bacteria, the delicate chemistry of oceans and soil. No volcano, lightning strike, or mineral reaction could forge it. Only life could. His hands trembled as he reran the calculations, searching for any error, any instrument glitch that might explain it away. None appeared. The numbers held. The signal persisted. Across the void, 120 light-years from Earth, a planet was exhaling proof of its existence. The realization spread quietly at first, rippling through research teams connected by encrypted channels. Those who saw the data reacted not with disbelief, but with awe, as though they had collectively stepped beyond a threshold that humanity had been approaching for centuries. It was the first whisper of confirmation that the loneliness of our species had never been absolute. Yet the implications were too vast to grasp all at once. Before the public could know, the data had to be tested, retested, and stripped of every possible doubt. Webb's instruments were built to detect the faintest traces of molecules by observing how starlight changes as it passes through an atmosphere. Each atom absorbs light at specific frequencies, leaving behind spectral shadows like musical notes on a cosmic score. When Medusan compared the pattern to Webb's catalogue of known molecules, the match was undeniable. Dimethyl sulfide, clear and sharp, standing amid a chorus of water vapour, methane and carbon dioxide. A chemical ensemble that, taken together, resembled not chaos but equilibrium, the self-regulating breath of a living world. The magnitude of it pressed against the limits of imagination. For generations, humanity had scanned the skies, searching for a reflection of Earth, a second blue marble orbiting a yellow star. But what Webb had uncovered was something different, something perhaps even more promising. A planet 8 times Earth's mass, wrapped in hydrogen, circling a quiet red dwarf whose light would outlive galaxies. The conditions were improbable, yet somehow perfect. As the data solidified, the team calculated the probability of error. It was less than 3 in 1,000. Statistically, the signal was almost certain, and yet no number could capture the emotional gravity of that conclusion. For Medusan, it wasn't a triumph of career or competition, it was a moment of communion. The light reaching his instruments had begun its journey, when human civilization was barely touching the age of flight. Now, after 120 years wandering the void, it had returned carrying the scent of another ocean, the breath of another biosphere. In that instant, the distance between worlds no longer felt insurmountable. The stars, once symbols of mystery and absence, became mirrors reflecting our own existence back at us. The universe, for the first time, seemed less like a stage for isolated observers and more like a living network whispering across time. The discovery didn't shout. It murmured a single molecule, soft as breath, declaring across the dark, "You are not alone." The morning the numbers arrived, Cambridge was still asleep under a haze of winter rain. The observatory's servers hummed quietly, their processors working through the night to decode the light that had crossed interstellar space. Niku Medusan entered his lab before dawn, carrying a cup of coffee gone cold by the time he reached his desk. On his monitor, a set of graphs traced the faint oscillations of brightness from a red dwarf star in Leo, its light dimming in perfect rhythm as something massive passed before it. Each transit meant an orbit, a world eclipsing its parent star for a fraction of a second. But this time, the data felt different, cleaner, sharper, and charged with an energy he could not explain. He had seen hundreds of exoplanet spectra before, but none had carried this peculiar symmetry. At first glance, the numbers told a familiar story. A sub-Neptune world cloaked in thick gases, circling a small sun too dim to warm it in any way that Earth's biology could endure. Yet something in the light curve refused to behave according to expectations. There was a pattern hidden within the spectrum, a molecular signature buried in the noise, like a whisper beneath static. Medusan adjusted the filters, isolating wavelengths absorbed by the planet's atmosphere. As the algorithm stripped away interference, a set of sharp absorption lines appeared where none should be. He blinked, thinking it a calibration error. Then he compared it to Webb's spectral library, and felt his pulse quicken. The pattern belonged to dimethyl sulfide, a compound produced only by living systems on Earth. It was the invisible perfume of life released by plankton drifting in the ocean, by microbes in the soil, by decay and regeneration in equal measure. No geology could imitate it. No volcano or lightning storm could fake its shape. The signal repeated itself through multiple observations, steady and consistent, each time the planet passed before its star. That repetition was what made it undeniable. Noise never repeats. Life does. He stared at the data long enough for the room to lose its boundaries. The world outside the window dissolved into fog. Somewhere across 120 light-years of emptiness, a planet was breathing, its exhalations captured in light and carried to his screen. The probability of coincidence was infinitesimal, a margin so slim it made skepticism feel more irrational than belief. 3 in 1,000, that was the estimated chance that the reading could be wrong. Not certainty, but close enough to shake the pillars of everything humanity had assumed about its solitude. Medusan printed the first spectral graphs and spread them across the lab table. Around him, the silence of the building deepened. He imagined the photons that had started their journey in the age of gas lamps and horse-drawn carriages, finally arriving to paint this delicate proof. Each photon, an ancient messenger, each wavelength, a syllable in a story told across a century. He called in his research partner, and together they began cross-checking every potential source of contamination. Could the signal have come from Earth's own atmosphere? No, the telescope's vantage point at L2 was far beyond such interference. Could it have been a reflection from the instruments? Impossible. The pattern stability ruled that out. One by one, every alternative hypothesis collapsed. What remained was biology, a planet alive. The official designation, K2-18b, sounded sterile, mechanical, unworthy of the enormity of what it represented. Medusan found himself thinking of it instead as a mirror one that didn't reflect light, but existence. When word of the anomaly reached NASA's Exoplanet Analysis Group, they reran the data independently. The results were identical. Dimethyl sulfide at measurable levels, along with water vapor, methane and carbon dioxide, a cocktail of gases that hinted at complex chemical cycles, not the dead equilibrium of sterile worlds. The combination was elegant, balanced, like a planet inhaling and exhaling in rhythm with its star. Over the next weeks, the confirmation process became an obsession. Data teams across continents aligned their methods, comparing every wavelength, recalibrating every uncertainty. The more they analysed, the more the signal clarified. In a field accustomed to ambiguity, this level of consistency felt surreal. "It's not just noise," Medusan whispered during one late-night session, his voice half disbelief, half prayer. "It's behaviour." That single word captured the essence of what made this so extraordinary. A planet with chemistry that behaves. It reacts, adapts, resists stasis, the hallmarks of life itself. For centuries humans had asked whether life existed elsewhere, but the question had always been philosophical. Now, under the cold hum of laboratory lights, it was empirical. The discovery did not announce itself with fanfare. It emerged like dawn, slowly, inevitably, turning speculation into measurement. Every scientist who touched the data felt the same quiet awe, that the universe, after keeping its silence for so long, had finally spoken. And what it said was both humbling and beautiful, that life is not a miracle, but a pattern written into the physics of existence. The story had begun not in poetry or myth, but in photons, and for Medusan, sitting in the dim glow of his monitor, it was as if those photons had carried across the void not just information, but recognition, a message hidden in the starlight that had waited 120 years to be heard. When the confirmation came, it arrived not with celebration, but with silence, a kind of collective stillness that spread through the teams analysing the data, the moment when everyone realised the implications were too vast for words. Across research centres from Cambridge to Pasadena, scientists sat before their screens watching the numbers align with impossible precision. Dimethyl sulfide, the molecule no one expected to find beyond Earth, a signature of life, clear and sharp, etched into the light from a world 120 light-years away. On Earth, that same molecule drifted above plankton-rich oceans and humid forests, rising from the metabolism of creatures so small that billions could fit into a drop of water. It was not the smell of grandeur, but of persistence of life quietly continuing, unseen and unending. For centuries, astronomers had looked for signs of oxygen, methane or water as the hallmarks of habitability. But dimethyl sulfide was different. It was not merely compatible with life. It was life's direct announcement, a molecule born from living breath. No geological or chemical process could mimic it. Lightning, volcanic gases, radiation, all had been tested, and none produced its spectral fingerprint. On Earth, it existed because biology insisted upon it. Now, the same spectral lines appeared in the atmosphere of a planet orbiting a faint red sun. The first thought was disbelief. Perhaps the data had been contaminated. Perhaps an artifact of the sensors or a stray reflection had fooled the algorithms. But as every test confirmed the result, disbelief gave way to something far greater wonder. Medusan's team gathered in the observatory's main lab late one night, surrounded by glowing monitors displaying spectral charts that looked like music sheets written in light. The pattern was unmistakable, its rhythm repeating with mathematical precision every time the planet crossed its star. "It's breathing," someone whispered, and no one argued. The evidence suggested a living chemistry, an atmosphere sustained not by accident but by balance. Methane, carbon dioxide, and water vapour formed a dynamic equilibrium, never settling, always shifting, just as Earth's own air did because of the ceaseless work of living things. That imbalance, scientists realised, was the key. On a dead world, gases stabilise into predictable ratios, reaching a silent equilibrium. On a living one, those ratios dance, never still, because organisms are constantly reshaping them. Webb's instruments had captured that dance, a chemical choreography across a planet's skies. Even the absence of certain molecules spoke volumes. Ammonia, which should have accumulated naturally, was nearly missing, perhaps consumed by biological processes that converted it into more complex compounds. The planet was not merely habitable, it was active. The data suggested something happening on a planetary scale, an ecosystem sustained by chemistry and time. The idea that such a world might exist had always been a scientific daydream, the kind of speculation reserved for conferences and science fiction novels. Now it was measurable. Humanity had crossed a boundary without realizing it. We were no longer looking for possibilities, we were reading confirmations. The numbers didn't just imply life, they described it. Medusan leaned back from his console, overwhelmed by the scale of it. The signal that had taken a century to reach us was already old by the time it was captured. Whatever had produced it might still exist, or it might have evolved, changed, or vanished. What Webb had seen was the past, a living echo preserved in photons. That thought alone made his chest tighten with awe. For the first time, humanity wasn't just discovering another planet. It was encountering the memory of another biosphere, a snapshot of existence from a world long beyond our reach. The 99.7% confidence statistic, so clinical on paper, suddenly felt almost spiritual. In physics, that level of certainty was used to confirm the existence of particles or gravitational waves. But this was something different. This was evidence of life. It meant that in the cold equations of the cosmos, biology had become a measurable constant. The discovery shattered the notion of cosmic silence. The universe was no longer indifferent. It was responsive. Light itself had become a messenger, carrying across the dark a message as old as chemistry, that life is not confined, that it seeks expression wherever the conditions allow. When the news quietly reached other institutions, some scientists reacted with disbelief, others with tears. The search for life had always been humanity's oldest question, a longing disguised as research. And now, through the lens of a telescope orbiting in eternal shadow, the answer had finally arrived, not shouted, not proven by contact, but whispered through the language of molecules. Dimethyl sulfide was the universe's way of saying that creation had repeated itself. Somewhere beyond our blue world, in a sea of hydrogen and light, life had taken root. It had endured, grown, and exhaled just as we do. That realization did not reduce the mystery, it deepened it. Because if life could emerge there beneath a crimson sky around a small, steady star, then it could emerge anywhere. And if it could emerge anywhere, then the cosmos was not empty but alive in ways we were only beginning to imagine. Medusan knew that centuries from now, historians would look back at this moment as the quiet turning point when science crossed the final threshold of solitude. Humanity had found not its twin, but its kin. The confirmation didn't come in the form of a broadcast or a signal. It came in the faintest chemical breath drifting through space. Caught by golden mirrors a million miles from home, a molecular murmur from the dark, declaring across the ages that existence, once begun, refuses to end. They named it K2 18b, a title so mechanical it seemed almost to insult the poetry of what it represented. Yet behind the sterile alphanumeric tag lay a world that rewrote the definition of what habitable could mean. 8 times the mass of Earth, and more than twice its size, this exoplanet orbited a faint red dwarf in the constellation Leo, a modest star that shone not with brilliance, but with endurance. To the naked eye, the star was invisible, lost among the countless points of light that pepper the winter sky, but to Webb's instruments, it was a treasure chest of spectral gold. The planet that circled it was neither a gas giant nor a terrestrial sphere. It belonged to a rare and fascinating class, a sub-Neptune, large enough to retain a thick atmosphere, small enough to avoid collapsing into a storm-wrapped colossus like Jupiter. For years, such worlds were dismissed as unfit for life. Their hydrogen-rich atmospheres were thought to crush the possibility of oceans or air pressure compatible with biology. Yet Webb's measurements revealed a paradox. Beneath that dense shroud, the temperature held steady at around 49 degrees Celsius, a condition so specific it seemed calculated for balance. Warm enough to allow liquid water, cool enough to preserve it. The hydrogen acted as a thermal blanket, redistributing energy evenly across the globe. Unlike the violent weather systems of gas giants, K2-18b's climate appeared stable, calm, self-regulating. It was as if the planet had discovered its own equilibrium long before we arrived to witness it. The more data Medusan's team gathered, the clearer the picture became. Each transit across the star allowed starlight to pass through the planet's atmosphere, carrying the chemical fingerprints of its composition. First came the expected signs: water vapour, methane, and carbon dioxide, familiar companions in the atmospheres of countless exoplanets. But the ratios here told a different story. These gases did not exist in chemical equilibrium. They fluctuated in a delicate dance that suggested constant renewal. On a lifeless world, such elements would react and settle into balance, but on K2-18b, something was maintaining their imbalance, a planetary metabolism. The more they studied the numbers, the more it seemed like a living system in motion, one capable of sustaining itself over immense spans of time. The discovery of dimethyl sulfide only amplified that impression, marking the world not as merely habitable but inhabited. Scientists had long sought an Earth twin, a rocky sphere, bathed in the yellow light of a sun-like star. Yet this planet defied that expectation entirely. It was not Earth-like at all, and perhaps that was what made it more extraordinary. Life, it appeared, did not require a mirror of home. It required stability, chemistry, and time. K2-18b offered all three in abundance. Its thick atmosphere was not a barrier but a womb, insulating its oceans from the harshness of space, and spreading warmth so efficiently that day and night scarcely mattered. Somewhere beneath that luminous veil, water could pool into endless seas, shimmering under the red glow of its parent star. The idea of such oceans stirred something ancient in every scientist who saw the data. For the first time, the concept of alien seas was no longer metaphor or dream, it was probability. And those oceans, hidden beneath hydrogen clouds, could be hundreds of kilometers deep, dark and pressurized, yet rich with the chemistry that forms the building blocks of life. The sheer scale of it was staggering. An entire planet covered in liquid, warmed by a dim eternal sun, breathing out molecular traces of existence. If life had ever emerged there, it would not be fragile. It would be tenacious, patient, eternal. The more scientists modelled the planet's conditions, the more elegant its balance appeared. Its orbit kept it within the gentle cradle of its star's habitable zone, completing a revolution every 33 Earth days. That closeness, once thought to doom such worlds to extreme radiation, was instead a source of constancy. The red dwarf that anchored the system was quiet, no violent flares, no erratic outbursts, just a steady burn that promised stability for trillions of years. Compared to the brief volatile lifespan of our own sun, it was practically immortal. Around such a star, evolution could proceed not in frantic bursts but in endless continuity. If Earth was a song of survival, this world was a symphony of permanence. As the models rendered simulations of K2-18b's skies, scientists imagined what it might look like to stand there or to float, for there might be no solid surface at all. The sky would burn in gradients of crimson and violet, the horizon diffused by haze, the star frozen in the same spot, neither rising nor setting. The air would shimmer with density, heavy and luminous, thick enough to muffle sound and slow movement. The planet would exist in perpetual twilight, a world where day and night merged into an eternal dusk. Life, if it existed there, would adapt to patience, not haste. Energy would be scarce, but time would be infinite. Plants, if one could call them that, might drink red light instead of yellow, absorbing every faint photon through dark pigments of indigo or black. Creatures might perceive their world through vibration rather than sight, sensing the pulse of the planet rather than its colour. In that calm, enduring environment, evolution would favour resilience over aggression, cooperation over speed. The more we imagined it, the more it seemed that K2-18b was not a mirror of Earth, but its counterpoint, a reminder that life's creativity is not bound by familiarity. As Meduson watched the data cascade across his screen, he realized that the planet's name no longer mattered. It was no longer just K2-18b, it was proof that nature's imagination exceeded our own. In science, numbers are sacred. They separate belief from knowledge, illusion from evidence. When Meduson's team calculated the probability that the signal was false, the result seemed almost implausible. 99.7% certainty, a figure that in physics marks the threshold of discovery. It was the same statistical confidence once demanded to prove the existence of the Higgs boson or gravitational waves. In a field built on caution, this level of precision was not a suggestion, it was a declaration. The odds of error, 3 in 1,000, were so minuscule that denying the conclusion required more faith than accepting it. What they were witnessing was not noise, not coincidence, but the most credible evidence of extraterrestrial biology ever recorded. The room where the calculation appeared on screen fell utterly still. Someone whispered the number aloud, as if hearing it might make it more real. 99.7. The figure seemed too exact for something so vast, too simple for a discovery that would rewrite history. But science thrives on simplicity. on clean probability that cuts through the fog of speculation. For centuries, humanity had asked whether we were alone, phrasing the question as poetry, religion, or philosophy. Now the answer arrived in the syntax of mathematics. 3 significant figures, 1 decimal point, and a universe transformed. Yet the scientists who held that knowledge did not cheer. They understood too well what it meant. Certainty in data does not bring clarity to meaning, it brings weight, it carries consequence. For weeks, Medusan could barely sleep. Every time he closed his eyes, he saw the smooth curve of the light graph, the delicate dip marking the planet's transit, the rows of numbers glowing like a secret language. Each value was a promise that the universe was not a silent void but a living continuum. He knew how rare such confidence was in astronomy. The cosmos is a master of illusion. Noise masquerades as signal, stars masquerade as planets, and human hope often fills the gaps in measurement. But this was different. Webb's data was pristine, its precision unassailable. Every test performed by independent observatories produced the same result: dimethyl sulfide at levels impossible to ignore, methane, carbon dioxide, and water vapor interwoven in perfect imbalance, the same imbalance life creates on Earth. It wasn't merely that the data was correct, it was that it was consistent, a word that in science carries the weight of truth. And yet, beneath the statistics, something deeper stirred. The recognition that numbers, for all their certainty, could never convey the enormity of what they confirmed. The percentage told them that biology was almost certainly shaping the atmosphere of K2-18b, but it could not describe what that biology looked like, how it moved, how it perceived its world. The telescope could measure the breath of life but not its face. The reality of that paradox haunted the researchers. They were the first humans to know, truly know, that life existed elsewhere, and yet they could not see it, touch it, or even imagine it clearly. Their only connection was mathematical, the universe's most honest language. And perhaps that was enough. Over the next days, scientific forum buzzed with restrained astonishment. Data verification teams, accustomed to skepticism, found themselves unable to dismantle the results. Every statistical model held, every potential error collapsed under scrutiny. The signal was not a fluke, it was a fact. The certainty grew so overwhelming that disbelief no longer felt rational. Still, official announcements were postponed. The data needed to survive peer review, replication, and the unforgiving rigor of global analysis. Behind closed doors, however, the implications began to bloom. If one planet, just one among the thousands Webb had scanned, showed a chemical fingerprint of life, then the universe was not a sparse gallery of dead worlds, but a vast ocean of biology. The Drake equation, once a hopeful abstraction, suddenly seemed too conservative. The probability of life elsewhere was no longer a question of if, but of how often. Medusan thought about that as he walked home through the quiet streets of Cambridge, snow falling like ash under yellow streetlights. The world around him seemed both smaller and infinite. Humanity had spent centuries defining its loneliness, building philosophies around the assumption of isolation. But now the sky had answered back. The cold air on his face, the glow of windows, the hum of distant traffic, all of it felt newly connected to something immeasurable. When he reached his door, he glanced up at the constellation Leo. Somewhere within that cluster of faint stars was a sun too dim for human eyes, and around it, a planet that might be watching its own skies. 99.7%. The number echoed like a mantra. It didn't just represent confidence, it represented contact. Not the kind sung of in myths or imagined by dreamers, but the quiet, undeniable handshake of physics and biology across the void. Humanity had always searched for certainty in the heavens, but what it found was something even more profound. Evidence that the universe does not waste its potential. Life, once thought miraculous, had become statistical, and yet, far from diminishing its wonder, that realization magnified it. Because if existence is inevitable, then meaning is universal. Every breath on Earth, every leaf that turns sunlight into sugar, every heartbeat that echoes in the dark, each is part of the same cosmic equation. Medusan smiled faintly at the thought. 99.7% was not just a measurement. It was the universe finally reaching statistical significance. To understand why K2-18b was so astonishing, one had to look beyond the numbers and imagine the physics of its survival. The planet's atmosphere was an immense cocoon, composed largely of hydrogen and helium, with traces of methane, carbon dioxide, and water vapor threading through it like veins in a living body. This composition created what the research team began to call the gentle greenhouse. Unlike Earth's carbon-heavy system, which flirts dangerously with instability, this hydrogen blanket maintained perfect balance. It captured the red dwarf's modest warmth and redistributed it evenly across the planet, turning what should have been a frozen wasteland into a realm of permanent spring. Temperatures that on Earth would scorch deserts or boil oceans instead existed here as constants, unwavering across centuries. The energy that reached the planet from its small calm sun was meagre, yet nothing went to waste. Hydrogen, being the lightest of gases, circulated heat globally, smoothing out extremes. There were no blizzards, no infernos, just a uniform warmth that could cradle liquid water in vast, endless basins. To Medusan's team, that stability was the signature of something profound. A planet in long-term thermal equilibrium, a world that had learned how to stay alive. They modelled the layers of its atmosphere, calculating pressure gradients and temperature curves, and what emerged from their equations was breathtaking. The upper layers shimmered like a mirror of faint metallic haze, scattering the red light of its sun into soft hues of violet and copper. Deeper down, the air thickened, growing dense enough that the distinction between gas and liquid began to blur. The simulation suggested that somewhere below those clouds lay oceans hundreds of kilometers deep, a mixture of water and hydrogen so compressed that it formed a new kind of sea, neither gas nor liquid, but something in between. Within that strange environment, the boundaries that defined sky and ocean on Earth simply vanished. They became gradients, layers blending seamlessly into one another. The planet was not a sphere of land and air, but an organism of fluid motion. Heat from the star entered at the top, diffused slowly downward, and returned upward through convection currents, keeping the climate eternally stable. It was a planetary circulatory system, pulsing gently across geological ages. On Earth, equilibrium is fragile, constantly threatened by eruptions, ice ages, and impacts. But K2-18b's design, if one could call nature's persistence design, seemed immune to chaos. Its star burned quietly, its orbit was steady, its hydrogen shell unbroken. That stability meant life, if it had begun there, would never have faced extinction as we know it. Evolution could proceed without catastrophe, uninterrupted like a song that never pauses. The greenhouse effect, so often a warning word on Earth, was here an emblem of peace. It didn't suffocate, it sustained. The hydrogen acted as an insulator, locking in not just heat but time itself. In the models, water existed in all its forms simultaneously, vapor, liquid, even supercritical fluid cycling endlessly between layers. Rain would fall not as droplets, but as mist, thick and luminous, descending through clouds that never dispersed. The same molecules that evaporated from the ocean returned hours later as gentle condensation, feeding the balance again and again. It was the universe's version of a heartbeat. Scientists began to suspect that chemistry in such conditions might produce complexity far beyond Earth's own evolutionary experiments. Hydrogen, after all, was not a barrier to life, but its ancestor. It was the simplest, most abundant element, the starting point of every organic molecule known. In K2-18b's depths, under crushing pressure and eternal warmth, hydrogen could combine with carbon, nitrogen, and oxygen in myriad ways. The ocean beneath those clouds might teem not with life as we know it, but with life as chemistry could imagine it, organisms that breathed hydrogen instead of oxygen, metabolized methane instead of sunlight, and evolved at a pace determined by patience rather than struggle. To imagine such life was to confront how parochial our definition of biology had been. We searched for twins of Earth, expecting familiarity, when perhaps life's truest expression lay in contrast. On K2-18b, the greenhouse was not a threat but a cradle, not a symptom of imbalance, but the mechanism of harmony. The deeper the models probed, the more elegant the feedback became. Heat rose, moisture condensed, gases exchanged in ratios that always returned the system to equilibrium. Even disruptions, solar flares, asteroid impacts, or volcanic bursts would dissipate harmlessly into the vast atmospheric sea. Nothing lingered long enough to break the cycle. That endurance fascinated Medusan. He saw in it a kind of cosmic wisdom, a stability achieved not through rigidity but through flow. The planet adapted to its star, and the star gave it constancy in return. It was an equation written not in mathematics but in temperature and time. He often thought of it as the opposite of Earth. Our planet lived fast and burned bright, while K2-18b existed in perpetual moderation. The more he studied its atmosphere, the more he envied its serenity. It was a world that did not need rescue, revolution, or renewal. It had already found balance. If life existed there, it would be born not in struggle but in peace. And perhaps that, Medusan thought, was the secret nature of life everywhere, to turn the chaos of physics into the calm of persistence, to transform heat into habit, and in doing so, to teach the universe how to breathe. At the heart of K2-18b's quiet miracle burned a small, unassuming red dwarf, an ember of a star whose faint light had endured longer than most galaxies' memories. To the human eye, it would not blaze, it would glow, dim and patient, casting its warmth not in brilliance, but in persistence. Unlike our own sun, which flares with energy and ages toward inevitable expansion, a red dwarf lives slowly, its fuel consumed so sparingly that it can burn for trillions of years. This was the secret behind K2-18b's stability, a parent star that refused to hurry, a sun whose very nature was time itself. Around such a star, evolution was not measured in millions of years, but in eons beyond imagination. Where our world's history was a restless narrative of upheaval and renewal, K2-18b's would be a hymn of continuity. Nothing rushed there. Light arrived in soft waves steady as breath, warming oceans that would never freeze and skies that would never clear. The same energy that might ignite chaos elsewhere produced serenity here. To Medusan, the red dwarf represented the universe's gentler design, a cosmic patience that our own violent star could never afford. He liked to think of it as the difference between a candle and a furnace. The candle's flame might be small, but it never falters. Its calmness is its endurance. When he calculated the luminosity of that red sun, he found that it shone with less than 2% of our sun's brightness, yet it radiated constancy. The planet's orbit lay close, completing a year every 33 Earth days, so close that one hemisphere was forever illuminated while the other slept in eternal shadow. From space, the world would appear as a sphere divided by twilight, a glowing crescent of crimson haze fading into an infinite night. Yet even on the dark side, the hydrogen atmosphere redistributed warmth so efficiently that no region froze. The world lived suspended between day and night, a planet of endless dawn. That perpetual equilibrium fascinated scientists. On Earth, change drives evolution seasons, disasters, extinctions, but on K2-18b, time itself was the great sculptor. Without cataclysm, without interruption, life could evolve like music unfolding without end. A red dwarf's steady glow gave biology the one gift it craves above all others: duration. If life had begun there, it might have been old when dinosaurs first roamed our world. It could have matured in peace, adapting not to survive chaos but to refine harmony. When Medusan tried to describe it to his students, he said, "Imagine a sunrise that never ends. Imagine an ocean that's had billions of years to think." The red dwarf's longevity did more than nurture stability. It redefined what habitability meant. Our solar system is fleeting by comparison. In 5 billion years, our sun will swell and consume its inner planets. But the red dwarf of K2-18b will still be burning softly long after the Milky Way reshapes itself. It is, for all practical purposes, immortal. That thought carried an unsettling beauty. It suggested that if life existed there, it would not face extinction but eternity. Civilizations might rise and fall, not in panic against their star's death, but in rhythm with its unchanging light. The pace of existence around such a sun would be slower, more deliberate. Growth would not be driven by crisis but by curiosity. Perhaps evolution itself would find new forms of intelligence not bound by urgency, beings who measured thought not in seconds but in centuries. In his notes, Medusan wrote that the red dwarf was not just a star, it was an idea, a reminder that creation does not always require explosion. Sometimes it is sustained by restraint. Energy, when spent slowly, can last forever, and in that slowness lies the potential for complexity beyond imagination. The quiet glow of that distant sun was, in its way, the universe's lesson in endurance. Astronomers once dismissed red dwarfs as too dim, too volatile, too close orbiting to host life. Yet every new discovery turned that skepticism inside out. Their dimness, once considered a flaw, became an advantage, allowing telescopes like Webb to study their planets without glare. Their small size meant that worlds orbiting them could hold tight, stable paths, immune to gravitational chaos. Nature, it seemed, had been generous in its simplicity. 3 out of every 4 stars in the galaxy were red dwarfs. If even a fraction hosted planets like K2-18b, then the galaxy was not silent, it was teeming. Billions of long-lived suns, each potentially nursing its own slow civilizations, its own biospheres older than our species. The realization that eternity might breed abundance made Medusan pause every time he looked through data. He began to see the cosmos not as a sequence of births and deaths, but as a continuum of persistence. In that light, our own civilization appeared fragile, a flicker, in comparison to the crimson stars that would still burn when our history was dust. Yet rather than despair, he felt reverence. For the first time, humanity had found a window not just into space, but into deep time. A red dwarf's patience was a mirror for the universe's calmest truth. That creation, given enough time, perfects itself. K2-18b's existence was not a coincidence. It was the inevitable result of time allowed to do its quiet work. And somewhere beneath its perpetual twilight, perhaps life had learned that same lesson, how to live not for moments, but for millennia. The revelation did not arrive in thunder or light, but in the quiet certainty of data. For generations, humanity had stared at the stars searching for reflection, waiting for an echo that would prove we were not alone. Yet when the moment finally came, it felt less like discovery and more like remembering something forgotten. K2-18b was no fantasy, no mirage of speculation. It was a confirmation that the cosmos itself was predisposed toward life. The implications rippled outward from Cambridge, from NASA, from every observatory connected to Webb's network, spreading across the scientific world with the slow inevitability of dawn. The first response was disbelief, not denial, but an overwhelmed silence that filled conference rooms and digital forums. It was the kind of silence that follows revelation, when comprehension struggles to keep pace with wonder. Humanity had expected that if life were ever found, it would be through some dramatic signal or image radio waves repeating in prime numbers, alien structures glinting in starlight. Instead, it came as chemistry, as the faint molecular exhalation of a planet wrapped in hydrogen, whispering across 120 light years. The irony was poetic. After centuries of searching for voices among the stars, we had heard life not speaking, but breathing. Medusan found himself caught between euphoria and melancholy. He had devoted decades to the pursuit of this very moment, yet when it arrived, it felt both too intimate and too immense. In the solitude of his office, he read and reread the confirmed spectra as though the lines might reveal not only science but meaning. The data said nothing of what lived there, it only said that something did. That ambiguity both thrilled and unsettled him. Humanity's sense of uniqueness had always been fragile, but this was different. This was evidence that the universe was not indifferent. It was participatory. Life was not an exception, but an expectation. That realization reframed everything: philosophy, religion, art. All our stories of origin and destiny suddenly had to make room for another presence, unseen but undeniable. For the first time, the mirror we had always pointed skyward reflected back an image of companionship. Around the world, debates ignited in universities and think tanks. Was it appropriate to call K2-18b alive when no organism had yet been seen? Was it reckless to ascribe biology to molecules alone? But beneath the professional caution, the emotional truth was universal. Humanity had crossed the threshold of solitude. Even those who questioned the interpretation could not deny its power. The cosmos, once imagined as a frozen wilderness, now shimmered with potential. The discovery dismantled centuries of anthropocentric pride, replacing it with something humbler yet infinitely grander, a sense of belonging to a universe that cultivates life the way soil cultivates roots. When the news eventually leaked beyond the scientific community, the public's reaction was unlike anything before it. There were no riots, no panic, no apocalyptic dread. Instead, there was a strange and profound calm, as though the collective psyche of the planet had expected this all along. People gathered in parks, on rooftops, by the shores of oceans, staring into the night sky. Somewhere beyond their sight, another ocean was reflecting another sun. Musicians wrote symphonies inspired by the dim red light of that distant star. Poets compared humanity's discovery to hearing one's own heartbeat echoed in another chest. For a few rare months, the world seemed to breathe in unison. Politicians spoke of unity, philosophers of perspective, theologians of divine plurality. The discovery did not diminish faith, it deepened it. The universe had proven capable of more than anyone's doctrine had imagined. Medusan watched the global response with a mixture of awe and quiet amusement. He knew the excitement would eventually fade, replaced by bureaucracy, by mission proposals and funding battles. Yet for that brief interlude, Earth had glimpsed its own smallness and found beauty in it. What fascinated him most was how quickly people began to adapt to the idea. It was as if the knowledge had always been waiting just below consciousness, ready to bloom the moment proof appeared. In that sense, the revelation was not merely cosmic, it was human. We had always sensed that the universe was alive, we just needed permission to believe it scientifically. Astronomers began calling it the second Copernican moment. The first had displaced Earth from the centre of creation. The second displaced humanity from the centre of life. The emotional effect was identical humility followed by expansion. By losing centrality, we gained connection. The universe, far from shrinking in significance, became infinitely more intimate. Every star, every planet, every grain of interstellar dust now carried the possibility of kinship. Life was no longer a fragile anomaly, it was a cosmic principle. In his later lectures, Medusan would describe that realization as the moment the universe became plural. He would tell his students that the discovery of dimethyl sulfide on K2-18b was not the end of the search for life, but the beginning of the search for meaning. It was the first sign that existence was a dialogue, not a monologue, that the cosmos had always been speaking, and we had finally learned to listen. He understood now that the revelation's true gift was not proof but perspective. The stars no longer looked distant, they looked familial. Each one was a possibility, each orbit a question, each signal a heartbeat waiting to be recognized. Humanity, after millennia of calling into the void, had finally heard an answer. And the answer was simple, wordless, and universal. Life is not rare, it is inevitable. The discovery would never have been possible without the machine itself, the masterpiece of human engineering that had been launched into the void to see what no eye could see. The James Webb Space Telescope, its name spoken almost reverently among scientists, was not merely an instrument, but an extension of the human desire to understand. It floated 1 million miles from Earth at the Lagrange point L2, a position of perfect gravitational equilibrium, where the pull of our planet and the sun balanced precisely. There, in the cold silence beyond the moon, it unfolded its golden mirrors like petals of a mechanical flower facing eternity. Every component, from its beryllium mirror segments to its ultra-sensitive infrared sensors, had been crafted to read the language of light written billions of years ago. Its architecture was both delicate and defiant, surviving temperatures near absolute zero while detecting the faint warmth of worlds across unimaginable distances. The machinery was not just precise, it was miraculous. When sunlight struck its gold-coated panels, it didn't reflect brilliance, but restraint. Webb did not look at light. It listened to it, teasing out vibrations invisible to human senses, hearing the harmonies hidden within the universe's quiet symphony. At its core was an idea older than civilization, that knowledge could be built from observation, that seeing was understanding. But Webb did not see in any ordinary sense. It gathered whispers, photons stretched thin by the journey through time, each one carrying the faint memory of its source. Those photons struck the telescope's mirrors and converged, forming spectra that spoke in lines and troughs, in shadows and absences. From those patterns, scientists could deduce composition, temperature, distance, and motion. It was a translation machine between physics and perception. Without it, K2-18b would have remained nothing more than an unnoticed flicker in the endless sky. The scale of precision required to detect a planet's atmospheric composition from light alone bordered on the divine. The difference in brightness between the star and the planet's signal was millions to one, yet Webb's instruments could isolate that faint modulation. During a planetary transit, when K2-18b passed before its star, a tiny fraction of light filtered through its atmosphere, carrying with it the signatures of the molecules it encountered. The telescope caught those traces, absorption lines only a few parts per million deep, and turned them into truth. The process was a ballet of physics and mathematics. The telescope's near-infrared spectrograph split the incoming starlight into its component wavelengths, while the mid-infrared instrument captured subtler features invisible to older telescopes. Every photon was catalogued, time-stamped, and translated into data points that became the raw material of revelation. Medusan often thought of Webb not as a machine, but as a mind, one that saw the universe not as pictures, but as patterns. Where human eyes crave colour and form, Webb perceived balance and rhythm. It found meaning in the imperceptible. Its mirrors, polished to atomic precision, reflected not just light but intent, the distilled ambition of a species determined to understand its own insignificance. For all its complexity, Webb was also an exercise in faith. The engineers who built it had never seen it work in space before launch. It was too delicate to test fully on Earth. When it unfolded in the vacuum, deploying its sunshield and aligning its mirrors autonomously, billions watched in breathless suspense. That it succeeded flawlessly still seemed to Medusan an act of grace. The telescope's perfection became an argument for hope, a reminder that humanity, for all its chaos, could still build something pure. Every byte of data it transmitted was a thread connecting imagination to reality. Each signal sent from its antenna travelled across the solar system, through the deep space network, to servers on Earth where scientists like Medusan waited. Those numbers, once decoded, were the telescope's voice, a metallic whisper carrying the news of distant suns. And yet, for all its technical triumph, Webb was also heartbreakingly fragile. Its instruments could be destroyed by a single stray particle, its orbit thrown by an unexpected gravitational tug. It was a solitary voyager in a place where rescue was impossible. That fragility only made its endurance more profound. In a sense, the telescope embodied the same paradox as life itself, delicate yet persistent, improbable yet enduring. The machinery of discovery had become a metaphor for the thing it sought. It was humanity's eye turned outward, but also inward, searching for reflection. Medusan sometimes wondered what it would mean for Webb to one day look back toward Earth with the same scrutiny. Would it see dimethyl sulfide here too, a chemical sign of its own creators? The irony would be exquisite, a machine built by life confirming life's existence elsewhere, only to realize that it too was part of the same cosmic equation. In the end, the machinery of discovery was more than hardware. It was hope made visible, golden and precise, drifting in the silence of forever. It was the universe observing itself through human invention, a bridge between matter and meaning. Webb was not just looking outward, it was teaching us how to see. The true miracle of the James Webb Telescope was not that it saw light from distant worlds, but that it could interpret that light as language. Every atom in the universe leaves its mark upon the light it touches, altering its spectrum like an artist mixing pigments on a canvas that stretches across space. To the untrained eye, those changes are nothing more than fluctuations in brightness, tiny dips in a graph, unremarkable as static. But to Medusan and his team, they were sentences written in the dialect of physics. Each molecule absorbs light at particular wavelengths, leaving behind shadows in the starlight that passes through a planet's atmosphere. Those shadows, faint and precise, form the spectral fingerprints of matter. They are the universe's own handwriting. When Webb turned its golden eye toward K2-18b, it was not seeing an image but reading a signature, an intricate calligraphy of absorption lines that together revealed the chemical identity of an entire world. In those lines, the planet's story unfolded: methane's soft valleys, carbon dioxide's sharp peaks, water vapor's rhythmic curves, and then the delicate, unmistakable trace of dimethyl sulfide, a note so rare that it might as well have been a word. To capture such detail required patience and near impossible precision. During each transit, the telescope recorded minute differences in starlight intensity, translating them into data so subtle that even a single photon could shift meaning. It was the closest thing to listening to a heartbeat through the roar of a hurricane, yet Webb heard it clearly. Its sensors measured temperature and density variations across wavelengths invisible to human senses, constructing not just a list of molecules but a portrait of atmosphere, a living ecosystem painted in infrared. When Medusan overlaid the data sets from multiple transits, he saw the spectral lines aligning perfectly, like the chords of a melody repeating without distortion. The consistency confirmed that the readings were no illusion. They were the fingerprints of chemistry guided by biology. Dimethyl sulfide stood out not just for its rarity, but for what it implied. It was not a stable molecule under most planetary conditions. It should have broken apart under ultraviolet radiation, dissipated into simpler compounds. Its persistence suggested renewal. Something was constantly replenishing it, producing it in real time. On Earth, that something was life. Algae, plankton, and bacterial colonies emitted it as part of their metabolism, releasing it into the atmosphere where it interacted with clouds and light. To see that same molecular whisper drifting above an alien ocean was to see the fingerprint of respiration itself, a breath captured in the light of another world. Webb's detectors transformed that faint trace into data graphs, into equations, and finally into comprehension. Each absorption line became a syllable in a universal tongue. The universe was not silent. It spoke in spectra. The realization struck Medusan with quiet reverence. He often thought of Webb's spectrograph as a kind of stethoscope pressed against the chest of the cosmos. Through it, he could hear the faint pulse of creation, steady and calm. He imagined each wavelength as a heartbeat, each photon a messenger from an ancient event, travelling through time to deliver the news that life was not a singular accident, but a recurring pattern. The process that produced those spectral fingerprints was so precise it bordered on poetry. Light left the red dwarf, passed through the planet's atmosphere, lost specific wavelengths to molecular absorption, and continued onward for 120 years before touching the telescope's mirrors. That journey of a century's duration was distilled into a data point, a single stroke in the grand image of existence. Medusan found himself humbled by the simplicity of it. The universe, in all its complexity, communicated through absence. It was the missing light, not the remaining, that told the truth. Humanity had learned to read the silence between photons and find meaning there. To most people, astronomy still seemed like a distant art, too abstract to feel personal. But to Medusan, each spectral line was a thread connecting mind and matter. It was proof that consciousness could bridge the gap between atoms and ore. He often lingered on the thought that somewhere, perhaps even on K2-18b itself, there might be beings capable of their own observations. Perhaps they too had instruments to measure the faint glow of their crimson sun and had wondered about the small yellow star far away. If so, perhaps their instruments had already seen us, our own spectral fingerprint floating across the cosmos, oxygen and methane betraying our existence. It was a humbling symmetry. Two worlds, separated by light years, each unknowingly decoding the other's breath. The very act of detection was connection. Webb, in its silent orbit, had not only uncovered the chemistry of another planet, it had also revealed a truth about perception itself. To observe is to participate. By measuring the fingerprints of that distant atmosphere, humanity had left its own fingerprint on the universe, a trace of curiosity, an imprint of awareness. Light and life had become mirrors of one another, reflecting endlessly through the darkness. As the data scrolled across his monitor, Medusan understood that this was not just science, it was communion. The telescope had read a signature written in light, and what it found was not foreign at all. It was familiar. It was the same story that every atom tells when arranged just right, the story of order emerging from chaos, of breath from chemistry, of being from the void. The fingerprints were proof that the cosmos remembers itself. The more the scientists studied the atmosphere of K2-18b, the more it began to resemble a living organism rather than a mere celestial body. Its chemistry moved in cycles, not chaos. Methane levels rose and fell in rhythm with carbon dioxide, water vapour lingered in stable proportions, and the elusive dimethyl sulfide appeared in concentrations that fluctuated just enough to suggest renewal. It was as if the entire planet inhaled and exhaled with exquisite precision, maintaining a balance that spoke of metabolism on a planetary scale. On Earth, ecosystems function through exchange oxygen for carbon dioxide, carbon for energy, waste turned into nourishment. The data from K2-18b revealed a similar pattern, though expressed through different materials and under alien conditions. Instead of oxygen, hydrogen dominated the cycle. Instead of sunlight blazing through a blue sky, the energy source was the steady crimson glow of a red dwarf, its photons weaker but unending. In that soft light, the chemistry of life could proceed with patience rather than speed. The model showed that the gases interacted dynamically. Methane was being destroyed by ultraviolet radiation faster than geologic activity alone could replace it, yet the levels remained constant. Something was producing it. Simultaneously, carbon dioxide, which should have accumulated over time in such an environment, was instead partially depleted. Those two clues, an excess of methane and a deficit of carbon dioxide, mirrored what happened on Earth wherever biology was active. The equations described not chaos but cooperation, as though invisible actors were working in concert to preserve equilibrium. Medusan began referring to the phenomenon as the breathing system, a term that caught on in scientific papers and popular writing alike. The planet was no longer seen as a static sphere of gases, but as a dynamic environment, an interconnected web of chemical reactions sustained by continuous feedback. It was an alien ecosystem without a face, a biosphere that could be understood only through its influence on the air it shaped. If there were oceans beneath those hydrogen clouds, as simulation suggested, then they were not barren. Perhaps deep below, energy from the star and the planet's core met in the twilight layers, where temperature and pressure achieved the perfect compromise. There, organic molecules might gather, polymerize, divide, and reform, guided not by miracle, but by probability. Time was their ally. On Earth, life required billions of years to evolve from chemistry into consciousness. On K2-18b, beneath the gentle glow of a star that would burn for trillions, time itself was infinite. Given such abundance, complexity was inevitable. Scientists built models to simulate biological exchange within the atmosphere. They imagined microbial colonies floating in the dense air, feeding on chemical gradients instead of sunlight, perhaps metabolizing methane the way Earth's cyanobacteria consume carbon. They envisioned plankton-like forms adrift in perpetual twilight, absorbing energy from starlight so faint it would appear almost black to human eyes. Even without solid ground, life could thrive in suspension, buoyed by the thickness of the hydrogen air. There was elegance in the possibility that an entire biosphere might exist without soil or seafloor, a vast aerial ecosystem drifting endlessly between layers of gas and mist. The very density of the atmosphere, once considered hostile, would become a habitat, protective ocean of air. The concept overturned every assumption about where life could flourish. No longer was a rocky surface or oxygenated sky a prerequisite. K2-18b demonstrated that life's essential requirement was not environment but equilibrium. If the system could recycle matter and energy indefinitely, it could sustain life indefinitely. The distinction between planet and organism blurred further with every analysis. Medusan began to think of K2-18b not as a world that hosted life, but as a world that was alive. Its gases behaved like organs in symbiosis, exchanging and regulating with a precision no geology could mimic. Even storms, those inevitable products of heat differentials, appeared to follow rhythmic intervals, dissipating and reforming in cycles that hinted at self-regulation. To study such balance was to glimpse the architecture of nature's genius. Every planetary system, it seemed, sought stability, but K2-18b had achieved it perfectly. Its hydrogen blanket, far from chaotic, acted as a thermostat, distributing warmth and preventing extremes. Its atmospheric currents behaved like circulation, moving nutrients, if one could call them that, from the depths to the heights. The red dwarf's steady radiation acted like a heartbeat, driving the cycles gently, predictably, endlessly. The planet's ecosystem, if that word even applied, was a conversation between chemistry and light that had been ongoing for perhaps billions of years. humanity had simply stumbled upon it mid-sentence. Medusan often wondered whether consciousness, somewhere within that harmony, might have emerged not as an anomaly, but as a natural extension of balance, a mind born from stability instead of struggle. Perhaps intelligence, if it existed there, would be quiet, contemplative, shaped by the rhythm of eternity rather than the panic of mortality. It would not seek to dominate its environment, because the environment would already be perfect. That thought, both haunting and beautiful, stayed with him. In studying K2-18b, humanity had begun to glimpse not just another ecosystem, but another philosophy of existence. Life there, whatever its form, had learned to coexist with the universe instead of resisting it. It did not conquer entropy, it danced with it. The planet's breath was its wisdom. And in those faint fluctuations of methane and dimethyl sulfide, the universe revealed a secret it had held since its birth, that life is the ultimate act of balance. K2-18b was a planet that never truly knew day or night. Locked in tidal embrace with its red dwarf star, one hemisphere faced perpetual dawn, while the other remained buried in endless shadow. Between these extremes stretched a vast ring of twilight, a belt of soft, eternal glow, where the star hovered forever on the horizon. It was within this liminal region scientists believed that life might thrive. The light there would never blind nor vanish, and the temperature, moderated by the planet's dense hydrogen air, would remain constant across ages. It was a world of equilibrium, of slow transitions rather than sharp contrasts, where time unfolded not in hours but in moods. To imagine it was to imagine serenity made physical. The eternal day side of the planet glowed with a reddish luminescence, its clouds reflecting the steady pulse of the star like burnished copper. The air shimmered with density, scattering crimson light in every direction, until even the shadows glowed faintly. Far below, the upper atmosphere gave way to endless mist, layers upon layers of vapour that softened every outline and erased the concept of distance. The dark side, by contrast, was not dead but sleeping, a realm where starlight never reached yet warmth still lingered, carried across by atmospheric currents that refused to let anything freeze. The winds of K2-18b were slow and vast, flowing in continuous loops from the illuminated hemisphere to the dark, a planetary circulation that ensured stability. If one could stand upon that twilight band where light and darkness met, the sky would be an unending spectacle. The star would hover motionless at the edge of the horizon, painting the heavens in muted shades of red, violet, and gold. Clouds would drift in slow procession, glowing faintly from within, their undersides lit by the reflection of hydrogen seas below. There would be no sunrise and no sunset, only a perpetual in-between, a geography of hesitation. In such a place, the very notion of time would lose its meaning. Life would evolve not in cycles of night and day, but in the gentle constancy of twilight. It would adapt to a world that never slept and never woke, where photosynthesis, if it existed, could proceed endlessly under the same dim illumination. Perhaps organisms there would absorb energy not in bursts but in gradients, their metabolism tuned to the slow rhythm of eternity. On Earth, movement-defined survival creatures chase light, flee darkness, hunt, rest, awaken. But on K2-18b, existence itself would be steady, measured, serene. Medusan often wondered what it would mean for a species to grow up in such a place. Without the passage of days, without the drama of sunrise and sunset, would consciousness even conceive of time? Or would it live purely in the present, unhurried, unafraid of endings? The twilight belt, stable and unchanging, might foster minds that think not in events but in continuities. If intelligence arose there, it would not tell stories of beginnings or apocalypse. It would think in symmetries, in patterns as soft as its perpetual dusk. The tidal lock that once seemed a curse to astronomers now appeared as the planet's greatest gift. It guaranteed constancy, the same star, the same temperature, the same reliable division between light and shadow. It was a laboratory of balance. The substellar point, where the star hung directly overhead, would be warm enough to host thick clouds of vapour, rising like breath from unseen oceans below. As those vapours drifted toward the twilight region, they would cool, condense, and fall as luminous rain before evaporating again. The entire hemisphere might shimmer with slow, steady precipitation, droplets forming and dissolving in perfect repetition. The dark side, by contrast, could be home to calm, dense layers of atmosphere that trapped warmth like a blanket, protecting any chemical or biological processes taking place within its hidden depths. Nothing there would rush. Even the winds would move as if reluctant to disturb the peace. Every simulation the researchers ran reinforced the same truth. K2-18b was not a world of extremes but of moderation. It had turned the duality of day and night into a partnership, using the heat of one side to sustain the cold of the other. The planet's twilight zone was its heart, its habitable ring, a place where physics and poetry converged. When Medusan lectured about it, he would describe it as a world between breaths. He would tell his students that if life existed there, it would have evolved to see beauty in stillness, not in motion. Its eyes, if it had any, would be tuned to low light, sensitive to the subtlest variations in red and purple. Its senses would be slow, deliberate, attuned to the continuous hum of equilibrium. To such beings, the concept of darkness might be myth, and light something sacred but familiar. The eternal twilight would be both cradle and cathedral. In imagining this, Medusan realized that K2-18b was more than an astronomical discovery. It was a meditation on existence. The planet showed that creation does not always depend on chaos. Sometimes it thrives on calm. It taught that contrast is not always conflict, that harmony can emerge from perpetual balance. Between dawn and dusk, in that belt of soft light where the sun never rises and never falls, the universe had composed one of its most perfect symphonies. And somewhere within that melody, perhaps unseen even to Webb's golden mirrors, life might be listening, as patient and luminous as the light that sustained it. If life truly existed on K2-18b, it would not resemble anything Earth had ever imagined. The conditions of that world, its dense hydrogen atmosphere, its dim red sunlight, its unbroken calm, would shape biology in unfamiliar ways. To survive there, organisms would need to adapt not to change but to constancy. Evolution, in such a stable environment, would proceed not through crisis but through refinement. Instead of fierce competition, survival would depend on balance, cooperation, and persistence. Medusan often reflected that life, if it emerged beneath those endless clouds, would have evolved in the slow rhythm of patience. Without seasons or catastrophes to force adaptation, complexity could unfold gradually, layer upon layer, like coral building a reef over aeons. The creatures, or whatever form they took, would not be hurried by death or scarcity. They would be sculpted by abundance. Hydrogen, though light and elusive, could serve as both shield and resource. In the planet's lower atmosphere, where pressure was immense, hydrogen molecules might mix with carbon and nitrogen to produce energy-rich compounds. Perhaps life there used chemical gradients as its metabolism, feeding on the flow between hot and cold layers. Some scientists proposed that microbial colonies could drift like living balloons, buoyed by hydrogen, absorbing nutrients from the gases around them. Others imagined translucent planktonic structures, filaments kilometers long, floating through the air like airborne reefs. In the perpetual twilight, such life would glow faintly, their biochemistry producing soft radiance in hues of green and amber, biological response to the constant red light of the star. Photosynthesis, if it existed, would have adapted to the spectrum of a red dwarf, using pigments tuned to infrared wavelengths rather than visible light. On Earth, chlorophyll captures the high-energy blue and red photons of our Sun. On K2-18b, pigments might absorb in the deep crimson range, making the planet's skies shimmer faintly with the reflection of life itself. The entire twilight belt could glow from within, a slow pulse of bioluminescence echoing across the hydrogen seas. In the upper layers, life might take gaseous form entirely, amorphous colonies exchanging material and information through chemical trails, merging and dividing as needed. Their sense of individuality would differ radically from ours. Where humans define boundaries, these beings might see continuity. To them, life would be a network, not a hierarchy. Reproduction could be as simple as diffusion, identity as fluid as the air they inhabited. If intelligence had evolved in such a system, it would be collective, not singular, a consciousness distributed across atmosphere and motion. Communication might occur through changes in gas composition or electromagnetic pulses propagated through the thick air. Thought itself could manifest as chemical fluctuation, Medusan found that idea strangely comforting. Intelligence that never learned war because it never knew separation. A civilization that expanded not through conquest, but through diffusion. Evolution there would not reward aggression or dominance. It would reward equilibrium. The survival of one would depend directly on the balance of all. It was a model of existence the Earth had forgotten. The scientists studying the planet developed simulation after simulation, each more intricate than the last. Every plausible biological structure they conceived seemed to confirm one truth. Adaptation was universal, but expression was infinite. Life did not repeat forms, it repeated functions. Wherever chemistry allowed, it found a way to endure, to reproduce, to know. On Earth, life's strategy had been diversity. On K2-18b, it might be unity. Even in the absence of solid ground, intelligence could evolve from the dynamics of atmosphere, the way currents interacted, how energy moved, how information spread. To imagine such beings was to confront the limits of human imagination. Would they even perceive reality as we do? In a world without clear horizons, with no day or night, no beginning or end, perhaps perception itself would be continuous, their awareness flowing like their environment. There would be no need for memory, because nothing would change. Experience would be a constant present, self-renewing, self-sustaining. To them, time might feel circular, not linear or permanent now. Medusan speculated that if these beings existed, they might see our world as chaotic, unstable, even tragic. The constant cycle of birth and decay, the violent shifts of climate, the noise of civilization, such turbulence would be incomprehensible to minds born from stillness. They would find peace where we find monotony, wisdom where we find silence. In a strange way, studying K2-18b was like studying an alternate version of life's philosophy. Earth's evolution was forged by struggle, K2-18b's by patience. Both led to adaptation, but of very different kinds. Ours produced speed, creativity, and conflict. Theirs, perhaps, would produce harmony. The more Medusan pondered this, the more he began to sense that the universe might value variety not for competition, but for contrast. Each world, each ecosystem, expressed a different aspect of existence. Earth taught passion, K2-18b serenity. Between them stretched the spectrum of life's possibilities, and if we could one day learn from such equilibrium, perhaps we might evolve not biologically, but morally, learning from a world that had mastered what humanity still struggled to understand, how to exist without chaos. In his quiet moments, staring at the crimson graphs of spectral data, Medusan could almost imagine the whispers of that unseen life, drifting through the hydrogen winds, patient and content, wondering if somewhere across the dark there were others who still mistook motion for meaning. Once the first hints of biological chemistry on K2-18b were confirmed, the question that haunted everyone was inevitable. Could that world know we exist? For the first time in human history, it was not a philosophical musing but a scientific possibility. The idea that our instruments might not only detect life but be detected in return reshaped every conversation in the astrophysical community. The universe, which had long seemed deaf and distant, now appeared capable of dialogue. If living beings inhabited that hydrogen-wrapped planet, might they have built their own means of perception? Could their telescopes, or whatever equivalent they possessed, have already caught the faint signature of Earth's oxygen-rich atmosphere, our broadcast waves, our chemical fingerprints drifting across the void? The symmetry of it was intoxicating. Humanity had always looked outward, never pausing to imagine what it looked like from the other side. Perhaps, Medusan thought, the Watchers had been watching us too. Perhaps both species had been staring across light years, misinterpreting each other's silence as isolation. Webb's detection of dimethyl sulfide had proven that complex molecules could survive in alien skies. That same principle meant Earth's own biosignature methane, oxygen, ozone was radiating into space, an open invitation to any eye sensitive enough to see. In that realization lay both wonder and vulnerability. We were no longer hidden. For centuries philosophers had speculated about cosmic neighbours, but now the debate was no longer hypothetical. The numbers demanded seriousness. K2-18b, with its habitable conditions, orbited a type of star that made up 3/4 of the galaxy's stellar population. If even a fraction of such planets nurtured life, then the universe was not sparse. It was teeming. Every twinkle of red light in the night sky could be a home. Yet even with this probability, communication remained nearly impossible. The distance 120 light-years meant any signal sent today would not arrive until the 23rd century. The exchange would take generations, each answer a message to descendants. Still, the prospect was enough to ignite a quiet revolution in thought. If humanity could not speak to its cosmic neighbours, it could at least learn to listen better. Scientists began discussing how to refine detection methods beyond spectroscopy, how to search not only for molecules, but for structure, for the subtle order that might betray intelligence. Artificial emissions, rhythmic pulses, patterns in thermal radiation, these became the new vocabulary of the search. Some theorized that intelligent life on K2-18b might use chemistry itself as a medium of communication. Instead of sending radio waves, perhaps they altered their planet's atmosphere deliberately, creating detectable shifts in spectral lines as signals. It was a form of planetary-scale language, written not in words but in wavelengths. If so, then Webb's observation of dimethyl sulfide might not only represent life but intention. The notion was controversial. Many dismissed it as fantasy, but to Medusan, the thought lingered like a haunting chord. What if the pattern wasn't random? What if the planet had spoken first? For weeks he studied the data again and again, looking for repetition, modulation, anything that suggested rhythm. Nothing conclusive emerged, yet the idea refused to die. In the years that followed, new instruments would be proposed. Space telescopes capable of direct imaging, interferometers that could resolve continents on alien worlds. But even with those ambitions, the first signal remained a whisper, too faint to interpret, too subtle to dismiss. Humanity had touched the edge of comprehension but could not yet cross it. The paradox was almost cruel. We were close enough to know we were not alone, yet too far to know who the other was. And still, hope persisted. The act of searching, of pointing golden mirrors toward the dark, had changed what it meant to be human. We were no longer a solitary species confined to a blue world. We were participants in a cosmic network whose scope we were only beginning to perceive. The universe, once thought to be indifferent, was beginning to sound like a conversation. Medusan liked to imagine that somewhere above the clouds of K2-18b, a civilization might be conducting the same experiment, watching, measuring, wondering. Perhaps they too had detected faint signs of oxygen on a small planet orbiting a yellow star, and perhaps their scientists were even now arguing about what it meant. If so, then first contact had already happened, not through words or machines, but through mutual curiosity. Two species, separated by centuries of light, acknowledging each other's existence through science. In the end, that was communication enough. The signals across the void were not mere data, they were gestures of awareness. Each photon captured by Webb, each spectrum analysed on Earth, was part of that exchange. The cosmos was not silent, it was patient. It had been speaking in light all along, waiting for us to learn its grammar. The question of who sent the first signal no longer mattered. What mattered was that the dialogue had begun, and with it, the understanding that we were never isolated, only unready to listen. Medusan sometimes thought that perhaps the message was simple, encoded not in words, but in the very existence of both worlds. To be seen is to belong. As soon as the first whispers of potential communication arose, the excitement of discovery gave way to a deeper, more troubling question. Should humanity even try to respond? The realization that we might not be alone forced not only scientific reflection, but moral reckoning. Every generation had dreamed of meeting another civilization, but few had considered the ethical weight of doing so. If K2-18b truly harboured life intelligent or otherwise, then we stood at a precipice that could redefine not just our knowledge, but our responsibility. Medusan found himself at the centre of the debate, invited to panels and councils that gathered scientists, theologians and ethicists under one uncertain mandate: decide how to greet the unknown. The discussions were fierce, though rarely loud. There was too much awe in the room for shouting. One camp argued that silence was the only moral stance. Humanity, they said, had no right to interfere with a world that had evolved in peace. Broadcasting toward K2-18b, even with the best intentions, would be intrusion and disruption of a biosphere untouched by our presence. We had already reshaped one planet, often carelessly. To impose ourselves on another, even by signal, would repeat the same arrogance on a cosmic scale. They called it the prime directive of the cosmos. Observe, but do not touch. The other camp, equally passionate, claimed that to remain silent was cowardice. If life existed beyond Earth, then communication was not invasion but kinship. Civilization itself, they argued, was built on the courage to reach out. To know and be known was the highest expression of intelligence. If the universe has given us neighbours, one philosopher said, it would be an insult not to introduce ourselves. The tension between curiosity and caution was ancient, but never before had it carried such consequence. Medusan sympathized with both sides. He understood the yearning to speak to answer that faint spectral whisper with a signal of our own, but he also feared the irreversibility of contact. The first message would not just represent humanity's science, it would represent its soul. What could we say that would not betray our contradictions, our capacity for wonder and destruction alike? The thought haunted him. The debate widened beyond academia. Governments convened committees, religious leaders issued statements, and the public began to argue in living rooms and classrooms across the world. Some imagined messages of peace encoded in prime numbers, universal mathematics meant to transcend culture. Others proposed silence disguised as humility, leaving discovery one-sided, at least until more was known. A few voices, quieter but persistent, warned of danger. History on Earth had shown that encounters between unequal civilizations rarely ended without harm. Even if K2-18b's inhabitants were benevolent, humanity's reaction might not be. Fear had toppled reason before, it could do so again. The question became not only whether we should reach out, but whether we were ready to. Medusan often recalled the image of Webb itself. Silent, observant, patient. It did not speak. It listened. Perhaps that was the model to follow. Observation was communication enough. To look was to acknowledge existence. To understand was to respect it. When asked to give his own opinion before an international assembly, Medusan spoke with measured restraint. Contact, he said, is not a message we send. It's a mirror we hold up to ourselves. Before we decide what to say, we must ask what we wish to be seen. The line echoed through media for weeks, quoted by scientists and politicians alike. It crystallized the realization that the decision to communicate was not technical, but existential. What story would humanity choose to tell the universe? One of conquest and division, or one of humility and curiosity? The ethics of contact became the defining philosophical question of the century. New branches of study emerged: astroethics, exocultural anthropology, the jurisprudence of interplanetary interaction. Theorists debated how moral law could apply to beings we had never met, to minds we could not imagine. Some proposed a universal charter of non-interference, a kind of cosmic environmentalism that would treat alien biospheres as sacred preserves. Others envisioned diplomacy across light years, arguing that communication itself could be the foundation of peace. Medusan watched as the debate matured from speculation to structure. Humanity was beginning to behave like a species aware of its place in a wider community. For the first time, we were considering not just our survival, but our impact. Yet even as policy evolved, the mystery of K2-18b remained unchanged. The dimethyl sulfide signal persisted in Webb's data steady, patient, unreadable. It neither intensified nor vanished. The universe offered no reaction, as though waiting for us to decide what kind of participants we wished to be. In the quiet of his study, Medusan sometimes wondered whether the silence itself was an answer. Perhaps the beings of K2-18b had faced the same moral dilemma long ago and chosen restraint. Perhaps their wisdom was measured in stillness, their communication encoded not in sound but in example. The thought filled him with a deep, humbling peace. It was possible, he realized, that the highest form of dialogue between civilizations was not noise, but mutual reverence. The ethics of contact might not be about speech at all. It might be about listening, endlessly and faithfully, until both sides understood that acknowledgement, in its purest form, is already communion. The discovery of K2-18b's possible biosignature transformed not only science, but the very consciousness of humanity. For the first time, the idea that we were not alone ceased to be speculation and became a matter of evidence, a line in a spectrum that whispered of companionship across the stars. It was as though a mirror had been placed before the species, reflecting not just what we had found, but who we were in the act of finding it. The echo was profound. Around the world, societies began to reinterpret their oldest stories in light of the new reality. Religion spoke of creation as vast and generous, not confined to a single world. Philosophers rediscovered humility. Even the arts seemed to shift their gaze skyward, as if seeking kinship through melody and colour. For centuries the stars had represented distance and longing. Now they represented dialogue. Humanity had entered a new psychological epoch, the age of plurality. We were no longer a solitary voice in a silent universe, but one harmony among billions. Medusan, ever the pragmatist, understood that revelation rarely changes behaviour overnight, yet even he could not ignore the subtle transformation creeping through everyday life. People began to treat the Earth differently. There was a renewed sense of stewardship, as if the awareness of other living worlds reminded us that our own was sacred too. It was as though the discovery had made us custodians not only of our planet, but of our reputation. If they are watching, a popular saying went, let them see kindness. It started as a joke, but it grew into a quiet ethos. Activists invoked it, teachers repeated it, and politicians adopted it with disarming sincerity. A single planetary narrative had begun to replace the fractured ones that had divided humanity for millennia. It was not utopia old conflicts persisted, but the tone had changed. War, environmental collapse, inequality, all began to seem smaller, pettier, when set against the vast perspective of life elsewhere. The discovery had made humanity self-conscious, as if caught mid-argument in front of a guest. Medusan often remarked that K2-18b had accomplished what diplomacy, faith and philosophy had failed to do. It had united humanity through awe. The simplest observation that another world breathed had reminded us of our shared fragility. He began giving lectures not only on exoplanetary science, but on what he called the sociology of wonder. He argued that humanity's next step was not technological, but emotional, the ability to perceive itself as part of something larger than history. He quoted often from ancient texts that spoke of cosmic order, from poets who imagined life among the stars before telescopes made it measurable. To him, the discovery was not a revolution but a return. We have always known, he told his students. The stars have always been mirrors. We only needed better eyes. The echoes of humanity reached beyond academia. In art studios and concert halls, creators began to reinterpret the cosmos not as emptiness, but as presence. Paintings depicted the twilight of K2-18b as a sacred landscape of endless equilibrium. Symphonies incorporated the numerical ratios of its orbit into their rhythms. Writers described the planet not as an object of study, but as a metaphor for peace, a world that had achieved what ours never could. Even fashion and architecture reflected the shift. Buildings inspired by orbital geometry, garments dyed in muted reds and golds reminiscent of the hydrogen skies. It was as though the discovery had given the species a new aesthetic vocabulary, one rooted in continuity rather than conquest. Yet amid the beauty, Medusan noticed something else, a kind of quiet melancholy. The knowledge that life existed elsewhere brought comfort but also distance. The universe had become intimate and immense at once. Humanity felt both connected and small. For some, that humility was unbearable. There were movements that rejected the discovery, calling it illusion or deception, arguing that life on Earth was miracle enough. But these voices, though loud, dwindled with time. Reality, persistent and patient, had a way of prevailing. The data did not argue, it simply existed, and in its existence lay transformation. Over the years, children grew up knowing that somewhere out there was not fantasy but fact. They drew red stars in their notebooks and spoke of exoplanets as casually as continents. Space ceased to be a frontier and became a neighbour. Humanity's imagination expanded in proportion to its awareness. The very language of progress changed, no longer mastery of nature, but dialogue with it. Medusan sometimes smiled at the irony. In discovering another world, humanity had rediscovered itself. The search for life beyond Earth had turned into a search for meaning within it. The echoes of that journey resounded through culture, law, and identity, shaping a civilization learning to see itself not as central, but as part of a greater conversation. It was subtle, fragile, unfinished, but it was real. The species had matured slightly, and perhaps that was enough. In his later writings, Medusan described this era as the adolescence of the cosmos. He believed humanity had finally reached the age where it could understand that wonder carried responsibility, that to gaze upon another world was also to be seen by it. The echo, once a distant signal across space, had become internal, a resonance in the human spirit that would not fade. K2-18b was no longer just a planet. It was a reflection of possibility, a reminder that the universe's most enduring truth was not isolation, but connection. And in hearing that echo, humanity had finally learned how to listen to itself. With time, the discovery of K2-18b evolved from a single event into an intellectual revolution. It was no longer just a triumph of astronomy, it became the cornerstone of a new worldview. Humanity's understanding of life, intelligence, and even consciousness began to stretch beyond the boundaries that had confined it for millennia. For the first time, the notion of the living was not restricted to the biosphere of Earth, but applied to the universe itself. The cosmos was not a static backdrop, it was a participant. Every star, every molecule, every gravitational whisper could now be interpreted as part of a vast system of exchange. The realization that equilibrium could generate awareness, seen so clearly in the quiet balance of K2-18b reshaped philosophy and science alike. In universities, entire departments were reborn under new names: astroecology, cosmopsychology, quantum biogenesis. The walls between disciplines dissolved. Physicists collaborated with biologists, poets with data scientists, theologians with mathematicians. The quest to understand K2-18b had revealed that no single field could claim ownership of truth. It required cooperation, not competition, the very principle the planet itself seemed to embody. The search for meaning became collective. Humanity, inspired by the planet's harmony, began to imitate it. Research no longer chased glory, it chased connection. Institutions once divided by funding and pride learned to share resources, data, and credit. The Webb telescope had proven that perspective could transform knowledge. Seeing beyond Earth forced humanity to think beyond ego. Medusan, now older and revered, became the quiet philosopher of this new era. His lectures drew audiences not for their technical detail but for their depth of reflection. He spoke of light as memory, of spectra as conversation, of science as empathy. "We used to think discovery meant conquest," he said in one of his final addresses. But K2-18b has shown us that discovery is participation. To know something is to become part of it. His words resonated far beyond academia. Governments, inspired by the cooperative model of the global observatories, began forming alliances not for defense but for exploration. The boundaries of nations softened before the shared horizon of the stars. Space agencies merged their missions, pooling technology and intellect. Humanity's next generation of telescopes was built not by a single country, but by the planet itself. They named the program Symbios, symbolizing unity through observation. Its goal was not colonization or expansion, but understanding. For the first time, exploration was guided by humility rather than hunger. The new instruments, vast arrays of satellites orbiting in synchronized geometry, were designed to map the atmospheres of thousands of exoplanets. They would listen, not shout, measure, not disturb. The guiding principle was simple: learn without interference. The legacy of K2-18b had made restraint a virtue. Even artificial intelligence, once developed as a tool of control, was repurposed for comprehension. Machine learning systems were trained not to exploit but to interpret, to recognize subtle correlations between cosmic data sets. These systems began to uncover faint chemical patterns, linking star systems separated by light years. The idea that planets might influence one another through dust, radiation, or magnetic resonance, the beginnings of a living galaxy, took hold. The universe, it seemed, was not a collection of isolated objects but a continuum of interaction. Understanding this changed everything. The old mechanistic view of reality gave way to an organic one. The cosmos was no longer seen as a machine but as a metabolism self-balancing, self-evolving. Life was not a rare anomaly. It was the universe's way of maintaining its own equilibrium. Humanity's own existence, once interpreted as chance, now appeared as participation in that greater order. People began to describe consciousness itself as a cosmic feedback mechanism, the universe observing its own patterns through sentient eyes. "We are not outside of nature," Medusan wrote in his final book, The Breath of Worlds. "We are its awareness." The expansion of understanding was not purely scientific. It was spiritual, though without dogma. Faith and reason no longer clashed. They harmonized. The old arguments, creation versus evolution, matter versus mind, lost their urgency. The cosmos had become both creator and creation, both cause and effect. Humanity, standing between Earth and K2-18b, realized it was a bridge between forms of awareness, the turbulent and the tranquil, the fleeting and the eternal. This understanding brought neither arrogance nor despair, but a quiet gratitude. To exist was to be part of something unimaginably vast yet intimately connected. The discovery had undone the myth of isolation forever. Humanity's place in the universe was not at the center, nor at the edge, but within the flow. Every observation of distant light was now recognized as an act of self-recognition, every spectrum a reflection of shared order. In that awareness, progress lost its old meaning. Advancement was no longer measured in conquest or speed, but in depth of comprehension. To expand understanding was not to expand territory, but perception. As the new telescopes unfolded in the void and humanity gazed once again toward the red light of K2-18b, Medusan's words lingered across generations. The universe does not demand belief, it invites participation. And in accepting that invitation, humanity had finally learned that to understand was not to control, but to belong. Long after the first data from K2-18b had transformed humanity's understanding, there came a quieter age not of discovery, but of reverence. The excitement that once fueled telescopes and theories matured into something slower, more reflective. People began to see the study of the cosmos not as conquest or curiosity, but as pilgrimage. The phrase, pilgrimage of light, entered common speech to describe humanity's collective journey toward awareness. A journey guided not by destinations, but by illumination. The first stage of that pilgrimage had been mechanical. Machines like the James Webb Telescope, born of ingenuity and patience, had carried our sight across the abyss. But as generations passed, technology became almost invisible, ubiquitous, perfect, silent. Humanity's gaze no longer needed grand instruments. Space had become an extension of thought. Observation was everywhere, embedded in networks of orbiting sensors that fed into planetary archives accessible to all. Children learned to navigate the cosmos as easily as geography. Stars were no longer distant, they were familiar neighbors, their names spoken with affection rather than awe. Yet the familiarity did not diminish the sacred. Instead, it deepened it. The more humanity saw, the more it understood how vast ignorance truly was. The light from K2-18b, still travelling faithfully across space, continued to reach Earth's instruments, now more precise than ever. Each new measurement seemed less like data and more like scripture. The dimethyl sulfide signal remained constant, a single unbroken note in the cosmic symphony, a voice that had been speaking for millennia, indifferent to whether anyone listened. Pilgrim scientists, poets, seekers would gather in observatories or under open skies to contemplate it. The ritual was simple. They would project the spectrum of the planet onto walls or clouds, watching its faint colours ripple across the dark. To them, that curve of light was not just a line of absorption, it was a pulse, the visible trace of existence elsewhere. In it, people found meaning. It was as though the universe had given them a mantra, a reminder that continuity is the highest form of faith. Over centuries, the concept of pilgrimage changed. No longer was it a journey to a holy place. It was a journey of perception. The faithful travelled inward, through understanding. The light from distant worlds became their guide, each photon a teacher crossing centuries to share its story. "We walk in their radiance," wrote one philosopher of the era, "and they, unknowingly, walk in ours." The exchange of light became the silent liturgy of the cosmos. Humanity, once desperate to announce itself, had learned the power of quiet participation. The great telescopes no longer sent messages, they listened. They mapped the universe not as territory, but as relationship. Each world was treated with the respect given to a living being. Exploration had become communion. Medusan's legacy endured not through technology but through thought. His writings were studied alongside sacred texts, his reflections quoted in both scientific papers and meditative chants. The line that defined the age was his: "To see is to join." The phrase appeared carved into the stone of observatories orbiting Earth, engraved on instruments bound for interstellar space, whispered in classrooms and temples alike. Humanity had become a species of witnesses, custodians of perception. The pilgrimage of light was not without challenge. There were still those who questioned its purpose, who saw in the reverence of the cosmos a kind of surrender. They asked why, after centuries of progress, humanity had turned from expansion to contemplation. But the answer was simple. Comprehension had replaced conquest. To understand the universe was to participate in its serenity. The old ambition to colonize had faded, replaced by the wish to coexist. It was said that when a society matures, it stops asking what it can take from the stars and begins asking what it can give. Humanity had reached that threshold. Artifacts, messages of peace, repositories of knowledge were launched not to claim space but to honor it. They carried no commands, no boasts, only invitations, fragments of poetry, music, equations, and silence. Some were designed to decay gracefully, to dissolve into cosmic dust and rejoin the materials from which all worlds were born. It was a gesture of humility, an offering to the infinite. Pilgrims often spoke of K2-18b as the first teacher, the world that showed humanity how to listen. It was not worship they offered it, but gratitude. Every time the planet crossed its red dwarf star, sending that faint signature of life into the void, Earth received it as a reminder that consciousness was a shared inheritance, not an exclusive gift. As humanity's understanding deepened, exploration transformed from ambition into reverence. The stars were no longer targets to conquer, but destinations for pilgrimage. K2-18b, once just a point of data, became a symbol of humility, a reminder that discovery was not about expansion but illumination. The pilgrimage of light, as historians would later call it, began not with rockets but with reflection. People across the world turned their gaze upward, not in search of dominance, but in gratitude. The red glow of distant dwarfs became emblems of patience, their steady light inspiring movements of art, philosophy, and quiet devotion. Humanity had always sought transcendence, and now it found it not in temples or cathedrals but in telescopes. The journey outward had become indistinguishable from the journey inward. Medusan, though nearing the end of his life, watched this transformation with gentle pride. He often said that K2-18b was not a discovery of place but of perception. The universe had always been alive. We had simply learned to see it. In his final public address, he spoke to a generation that had never known solitude among the stars. "Once," he said softly, "we explored to prove that we existed. Now we explore to understand why." Those words captured the essence of the era. Pilgrims of knowledge replaced pioneers of conquest. Scientists, artists, and philosophers travelled together, not as rivals but as companions in awe. Each mission that launched into the void carried not flags but philosophies, statements of curiosity written in light and mathematics. The spacecraft no longer bore names of nations, they bore the names of virtues: patience, wonder, equilibrium, grace. Their missions were quiet, their achievements vast. Some mapped the molecular symphonies of exoplanet atmospheres, others captured images of starlight bending through alien clouds, or the silhouettes of worlds passing before their suns like slow-moving prayers. None sought glory. Every discovery was treated as a dialogue between the known and the possible. Humanity's exploration of the cosmos had matured into an act of listening. The pilgrimage of light extended beyond science. Artists began to follow the mission symbolically, composing works that blended data and emotion. Choirs performed sonatas built from radio frequencies of distant stars. Architects designed observatories that merged seamlessly with their landscapes, their roofs open to the sky as if inviting the universe inside. Even children, gazing through small telescopes, spoke of the stars not as destinations but as teachers. K2-18b, The distant world that had once been nothing but a whisper in light became the axis of this cultural awakening. Its crimson star was depicted in murals, literature and music as a symbol of endurance, a reminder that truth unfolds slowly, not explosively. The idea of a pilgrimage, of travelling toward understanding, resonated deeply in a world weary of noise. Humanity began to slow down. Progress no longer meant speed, it meant depth. The telescope data, endlessly refined, revealed subtler details, slight fluctuations in the planet's albedo, faint variations in cloud structure, a pattern of spectral changes that hinted at cycles longer than any human lifetime. Each discovery deepened the mystery rather than resolving it. That was part of the beauty. The further science reached, the more poetic its language became. Equations gave way to metaphors, and metaphors, in turn, guided new equations. It was as though the human intellect had learned to breathe with the universe, to expand and contract in sync with its pulse. The pilgrimage of light eventually inspired real voyages. New propulsion methods, powered by light sails and gravitational resonance, made interstellar travel theoretically feasible. The first unmanned probes were launched, carrying archives of humanity's art, music and mathematics. They were not messages of conquest, but of curiosity letters written in photons, addressed to whatever intelligence might read them centuries hence. Meduson's name was engraved on one of them, not as a hero, but as a witness. Before his death, he recorded a message that would accompany the probe, a final reflection to any who might find it. We came not to claim, but to see. In seeing, we found ourselves. The transmission, encoded in 10,000 languages and symbols, was both elegy and invitation. Generations later, when the probe passed beyond the heliosphere, people across the world watched in silence as its final signal faded. They called it the farewell light. In that moment, humanity understood something profound, that exploration was not escape but belonging, that every step into darkness was also a step into self-awareness. The pilgrimage of light was not about reaching K2-18b. It was about learning to travel with grace. The destination was understanding itself, radiant and infinite. And though no one yet knew if the beings of that distant world could see us, it no longer mattered. The act of seeking had become communion. In the glow of the red dwarf, filtered through clouds we had never touched, humanity saw not an alien planet but the reflection of its own awakening. The journey was complete, yet endless. The light that began in the constellation of Leo now burned quietly in human hearts. The legacy of K2-18b was not written in stone or data, but in the quiet transformation of how humanity saw itself. Centuries would pass, yet the moment Webb's golden mirrors caught the faint signature of dimethyl sulfide would remain engraved in memory as the dawn of awareness, a turning point when humanity stopped gazing at the stars as strangers and began to see them as kin. The discovery reshaped history, culture, and destiny in ways that even Meduson, visionary as he was, could never have imagined. It altered how we measured greatness, how we defined progress, and how we spoke of meaning. Before K2-18b, exploration had been a pursuit of frontiers. Afterward, it became a pursuit of connection. Before, we asked, what lies beyond? Afterward, we asked, what lies within? Humanity's greatest legacy was not that it reached the stars, but that it learned to see them as reflections of its own complexity. The planet became an emblem woven into civilization's consciousness. Its name appeared in textbooks, literature, hymns, and lullabies. Children learned to recite its coordinates as they once did constellations, and philosophers quoted its atmospheric composition like scripture. The phrase, to walk the K2-18b path, came to mean seeking balance, living with harmony rather than conquest. Its story became mythic, a world of hydrogen and twilight, a cradle of serenity that taught a restless species patience. The legacy was not bound to science alone. Entire ethical systems emerged around the lessons the planet represented. The doctrine of equilibrium, first proposed by Meduson's students, spread far beyond academia. It taught that progress should mirror the planet's calm growth without disruption, innovation without harm. Architects used its principles to design self-regulating cities powered by renewable cycles, while political thinkers adapted it into a philosophy of coexistence. Nations that had once competed for dominance began to collaborate on what was called the Planetary Covenant, a shared agreement to preserve Earth as carefully as we studied others. The shadow of the Anthropocene slowly receded, replaced by what historians would later name the era of reflection. Humanity no longer viewed the cosmos as a place to escape to, but as a reminder to tend what it already had. The idea that we might one day be observed by others, by those living beneath the red glow of K2-18b, became an ethical compass. Behave, a popular proverb went, as if the stars are watching. And in a sense, they were. Every beam of light leaving Earth carried traces of our actions, our pollution, our art, our voices, our violence. Awareness of this cosmic transparency changed us. History became less about domination and more about legacy, about what kind of light we would send into the universe. The planet's discovery had rendered humanity visible to itself. The arts flourished under this awareness. Painters depicted the hydrogen clouds of K2-18b as mirrors of emotion, endless gradients between red and violet symbolizing the continuum of being. Poets wrote of the eternal twilight as a metaphor for wisdom, the moment between knowledge and mystery where understanding truly lives. Musicians composed symphonies based on the rhythms of its orbital resonance, slow and meditative, as if imitating the pulse of creation. The legacy of K2-18b was not merely intellectual, it was spiritual. Humanity's relationship with existence itself matured. Religion did not vanish, it evolved. Faith began to describe the universe as sacred through participation, not separation. The divine was no longer imagined above the stars, but within them, as consciousness made manifest in matter. For many, K2-18b became the modern Eden, not a paradise lost, but a paradise remembered. It reminded humanity that balance was the original design of life, and imbalance merely a temporary forgetting. Generations grew up reciting Medusan's writings as both philosophy and prayer. Equilibrium, he had said, is not the absence of change, but the harmony of motion. His name became synonymous with cosmic ethics, his image carved into monuments that faced east, toward the constellation of Leo. The observatories that once hunted exoplanets became temples of understanding, where science and meditation were practiced side by side. The study of light itself became an act of devotion, yet for all the reverence, humanity never stopped questioning. The more we learned about K2-18b, the more we realized how little we understood. New telescopes revealed that the planet's atmosphere shifted subtly over decades, its molecular ratios dancing in patterns too complex for simple biology. Some believed it was weather, others suspected will. The mystery deepened, and with it, our humility. That too was part of its legacy. It taught us that wonder is eternal. To know everything would be to end the conversation, and the universe had no interest in endings. It preferred questions, endlessly renewing. K2-18b gave us one we could never fully answer, and in that, it gave us meaning. Long after Medicine's death, when the next generations built ships capable of approaching that distant system, they carried with them not conquest but reverence. They called themselves pilgrims, not explorers. They travelled not to claim, but to witness. When the first of them finally glimpsed the faint red glow of that far-off sun, the transmission they sent back to Earth was simple. We see it. It sees us. And with that, the circle of understanding closed not as completion, but as continuation. The legacy of K2-18b was that it made humanity eternal, not through immortality, but through awareness. In the end, the story of K2-18b was not about a planet at all, it was about connection. Across light years and centuries through silence and signal, humanity had reached beyond itself and discovered what it had been seeking all along, belonging. The cosmos, once feared as a cold and indifferent expanse, revealed itself as a web of relationships, each thread shimmering with the resonance of shared existence. Every photon that had ever travelled between stars carried the memory of that unity, binding the universe together in a language older than atoms. K2-18b was simply the point where we learned to listen. From the moment Webb caught the faint breath of dimethyl sulfide, a chain of understanding began that stretched through generations. It transformed science into empathy, exploration into introspection, and curiosity into communion. Humanity, once defined by its restlessness, had discovered the sacred art of stillness. In studying a distant world, we learned to inhabit our own. The discovery taught us that life is not a phenomenon confined to planets, but the essence of the universe itself, a continuity of consciousness expressed in infinite forms. Matter did not just exist, it remembered. Energy did not just move, it communicated. The cosmos was alive, and every living thing was part of its vast, ongoing conversation. The red dwarf of K2-18b still burned patiently, its light taking more than a century to reach us, yet it seemed nearer now than the clouds above our own skies. It was no longer just a distant sun, it was kin. Humanity's understanding of time changed too. The idea of separation dissolved when seen in the light of cosmic duration. 120 years, the distance between their world and ours became a heartbeat in universal time. We had not spoken to them yet, but the dialogue was already underway, woven through photons, equations, and imagination. The connection did not depend on language or technology. It existed in awareness. To know that another world breathed was enough. It was proof that existence was relational, not solitary. In that awareness, humanity found a peace no ideology had ever achieved. Earth itself began to mirror the balance it admired in K2-18b. Cities grew greener, slower, quieter. Progress was measured not by expansion but by harmony. Education shifted from the pursuit of knowledge to the cultivation of wonder. Every child learned that to study the stars was to study themselves. The light that once divided science from spirit now united them. The phrase cosmic connection became both philosophy and practice, the recognition that everything, from galaxies to grains of sand, was part of the same unfolding consciousness. In this new age, the cosmos was not out there, it was within, and every discovery was a rediscovery of that truth. Meduson's legacy endured not in monuments, but in the minds of those who followed. His writings, now preserved aboard ships travelling toward K2 or 18b, became sacred texts of a secular faith. The belief that awareness itself is holy. The universe, he had written, is not something to be understood. It is something to be remembered. His words became a mantra whispered in classrooms, observatories, and starships alike. When the first transmission finally arrived from the probe orbiting near the red dwarf, a faint signal, degraded but decipherable, it carried images of the twilight world itself, swirling clouds of bronze and rose, rivers of mist cascading through atmospheric layers, a horizon caught forever between dawn and dusk. Humanity wept when the pictures were revealed. The world they had imagined for centuries was real, and it was beautiful beyond measure. It looked both alien and familiar, as if it had been waiting for our gaze. In that moment the connection became complete, not as conquest or communication, but as recognition. The universe had looked back. Scientists spoke of feedback loops of light, photons that had left Earth centuries ago now reflecting off the atmosphere of K2-18b and returning faintly altered, as though carrying a message from the cosmos itself. You are seen. It was not a metaphor but a measurable fact. Earth's light and K2-18b's glow intertwining across the dark, each planet illuminating the other. The cosmic connection was not a myth, it was physics made sacred. Humanity's oldest yearning to be acknowledged by the universe had finally been fulfilled, not by words or visitors, but by reflection. We had found ourselves in the light of another sun. In the generations that followed, as humans journeyed outward and technology dissolved the boundaries between stars, this understanding remained central. The purpose of exploration was not discovery, but reunion. Every world found was a homecoming, every photon an echo of belonging. K2-18b had taught us that the universe is not a collection of separate worlds, but a single living continuum, each consciousness, each planet, each spark of awareness a note in its grand, endless harmony. And so, the story closed not with an ending, but a continuation. The red dwarf still burned, the hydrogen winds still carried whispers of unknown life, and humanity still listened. Across the gulf of space, two worlds existed in silent recognition, exchanging light as others might exchange breath. The cosmos had never been empty. It had only been waiting for eyes capable of seeing connection instead of distance. At last we had become those eyes, and as Earth turned beneath its own blue sky, bathed in sunlight that had once touched the edge of eternity, every being human or otherwise was joined in a single truth. The universe is aware, and through us it remembers itself.